Question 3. A beam AB has mass m and length 2a. The beam rests in equilibrium with A on a rough horizontal ground and with B against a smooth vertical wall. The beam is inclined to the horizontal at an angle theta as shown in figure 2. The coefficient of friction between the beam and the ground is mu. The beam is modelled as a uniform rod resting in a vertical plane that is perpendicular to the wall. Using the model, part A, show that mu is greater than or equal to a half cot theta. So, we're in mechanics, we're going to start labelling some forces on figure 2. Firstly, let's look at these reaction forces. There's going to be two reaction forces, one from the floor on the rod at point A, which I'll call RA, and one on the rod from the wall at B. So I'll call that reaction force B. And remember, reaction forces are perpendicular to the surface they are reacting from. Since this is rough horizontal ground, this rod here is not going to slip this way. And in order to stop it slipping this way, there must be some friction value which is working towards the wall. Our rod is uniform, and because it's uniform, its weight acts in the center. So this will be a distance from A, and its mass is m, and so its weight is mg, where g is acceleration due to gravity. This weight will have two components, one perpendicular to the rod and one parallel to the rod. This angle here would be theta. RA and RB would also have components parallel and perpendicular to the rod, and I've labelled where theta would be in each case. This could be useful because at some point we're likely to want to resolve parallel or perpendicular. And so with our forces labelled, let's start looking at left and right forces. So every force to the left is going to equal every force to the right because this rod is currently in equilibrium. And so to the left, the only force we have is RB, and to the right, the only force we have is friction. So we know that RB is equal to friction. If we look at taking moments around A, we can start to put RB in a different form of equation. So with moments, remember the anti-clockwise forces are going to be equal to the clockwise forces. So let's start with our clockwise force. The only clockwise force acting perpendicular to this rod is this component of weight, which is a distance times this component, which would be mg cos theta. So that's a mg cos theta is the clockwise force, and that equals the anti-clockwise force, which is this component from our reaction at B. And this component is 2a distance from A, and this is sine theta. So it's RB sine theta. So this equation is formed from looking at our moments about A. This can of course be divided through by A to give us mg cos theta is equal to 2rb sine theta. If we now choose to look up and down, we've got RA is the only force acting vertically upwards, and that must equal mg, which is our only force acting vertically down. And we're finding RA because what we would like to do, we've got our RB here, which we know to be equal to friction. It will likely be useful to substitute friction for something else, and because that's where we're going to bring in our inequality sign. Remember, friction is always less than or equal to mu times the reaction force. In this case, that's the reaction force at A, because this is the rough plane. This means then that friction is less than or equal to mg, because RA is equal to mg. And so since friction is equal to RB, that means RB is less than or equal to mu mg also. And now this can be substituted in place of our RB in this equation here, giving us mg cos is less than or equal to 2 mu mg sine theta. If we rearrange this now, we can divide both sides by the mg to give us 1 on both sides. And now we can divide by cos and divide by 2 to give us that mu is greater than or equal to cot theta. Remember, cos over sine is 1 over tan, which is cot theta. And this is what we want to show. A horizontal force of magnitude kmg, where k is constant, is now applied to the beam at A. This force acts in a direction that is perpendicular to the wall and towards the wall. Given that tan theta is equal to 5/4, mu is equal to 1/2, and the beam is now in limiting equilibrium, part B, use the model to find the value of K. Well, I've gone to the trouble of removing the previous friction from this diagram. The reaction forces and the weight all remain the same, but we now have this new force, kmg, which is working towards the wall. Since this force is now working towards the wall, our friction is going to be opposing it. And so our friction has changed direction. And we've been given a value of mu here of 1/2. So we have labeled our new diagram with our new forces. Start by looking left and right. This time I have two forces working to the left. I've got RB and friction, and I have the one force acting to the right, which is kmg. And so RB plus FR, the forces acting to the left, equal the force acting to the right, because this is in limiting equilibrium. We know friction is equal to mu RA. We are at the limiting extent of equilibrium now, so it's no longer less than or equal to. We know it is equal to mu RA. If we look up and down, RA remains unchanged. There's no additional up and down forces, so RA is still equal to mg as previous. Since friction then is equal to mu mg, that's substituting this RA into this equation here, and we're given that mu is equal to 1/2, then friction is equal to 1/2 mg. If we now look at taking a moments equation around A, the reason we're taking it around A is that all these forces, RA, FR and kmg, all have a moment of 0 because they are of no distance from A. And so the moments equation for A remains the same as it was previously. We only have the weight acting clockwise, which is mg cos theta, and that's times by A because of the distance of half the rod. And then we have the same reaction force B, and the perpendicular component of that is RB sine theta. If we divide this through by the A, which will cancel, and then the cos theta with the sine to get tan and the 2, it can be rearranged to show that RB tan theta is equal to 1/2 mg. Tan theta we know to be 5/4, and so 1/2 divided by 5/4 is 2/5, and so we've got the reaction force at B is equal to 2/5 mg. We now have RB as this 2/5 mg. We have friction as 1/2 mg, and that has to equal kmg from our very first left and right equation. Therefore, this expression here, the mg will cancel in each term, and so k will equal to 2/5 plus 1/2, which is 9/10.